Why would a doctor inject something radioactive into your body to find a disease, and then, weeks later, inject something radioactive again to treat it? Because nuclear medicine isn't one thing, it's a toolkit. And once you see how it's organized, the whole field suddenly makes sense. Start with a simple split. Everything in nuclear medicine does one of two jobs. It either helps a doctor see a disease or it helps them treat it. And the secret is that those two jobs need opposite kinds of radiation. To see, you need radiation that escapes the body, so a camera outside can catch it and draw a map. To treat, you need the exact opposite. Radiation that stops dead inside you, dumping all its energy on the target and going no further. Nature gives doctors four kinds to choose from. Gamma rays and positrons fly out of you. Those are for seeing. Beta particles and alpha particles stay inside. Those are for treating. And the choice gets beautifully precise. A beta particle travels a few millimeters, enough to blanket a whole tumor. An alpha particle stops in the width of 2 cells, precise enough to kill one cell and leave its neighbor untouched. So that's the map of the entire field. 2 jobs, 4 radiations. Everything else is just choosing the right one. Let's start with the hardest trick, photographing a disease from the inside. How do you take a photograph of something happening deep inside a living body with no beam fired in and no cut? You let the body glow and you listen. Inject a tracer that gives off gamma rays, and those rays pass straight out through you. A camera circles slowly, catching them from every angle, and a computer reconstructs a 3-dimensional map. The same maths a CT scanner uses, except the signal is coming from inside the patient. That's called SPECT. The atom that does most of this work is technetium. It glows for about 6 hours, enough to take the picture, short enough to fade fast. Around 40 million scans a year rely on it. But here's the catch. It can't be stockpiled, so it's made fresh every morning from a parent atom brewed in aging nuclear reactors. In 2024, 2 of those reactors went down at once, and scans were delayed worldwide. Then there's the sharper cousin, PET. Here, the tracer gives off positrons, antimatter. Each one meets an electron, both vanish, and 2 gamma rays shoot out in exactly opposite directions. A ring of detectors catches both and draws a line through the body. Millions of lines, one crisp map of where the disease is burning brightest. So now you can find it. But finding a cancer is only half the story. The real magic is what happens when the scan becomes the cure. What if the scan that finds your cancer could come back as the treatment, the very same molecule twice? That idea has a name, theranostics, and it's the most exciting thing happening in nuclear medicine today. The oldest version is almost a century old. Your thyroid hoards iodine, so doctors make iodine radioactive. A gentle form lights the gland up on a scan. A stronger form, swallowed as a pill, stays there and treats it. One element, it both finds and fixes. Now, modern chemistry has done the same trick for cancers all over the body. Take prostate cancer. Many prostate tumors wear a marker called PSMA on their surface. Doctors build a molecule that grabs only that marker, attach an atom that glows, and scan. Every deposit lights up. Then they keep the exact same molecule, swap in an atom that hits harder, and inject it again. It travels to the same cells and carries radiation right to them. The treatment is the scan, wearing a different atom.
The same approach now targets neuroendocrine tumors with a molecule called dotatate. See it with one atom, treat it with another. The scan literally draws the map for its own therapy. But what is that harder-hitting atom actually doing when it arrives? That's where you meet the two weapons of nuclear medicine and the frontier they're racing toward.
When it's finally time to kill the cancer, how does a doctor choose the weapon? It comes down to range, how far the radiation travels before it stops. The workhorse is beta radiation. It reaches a few millimeters, so it blankets a tumor and is forgiving if the aim isn't perfect. Lutetium is the beta atom behind today's biggest targeted therapies, and in the liver, doctors take it further, releasing millions of beta-emitting beads into the blood supply so the tumor irradiates itself from the inside. Then there's the sharpshooter, alpha radiation. An alpha particle carries enormous energy but stops in the width of 2 cells. That makes it brutally precise. Radium, which your bones mistake for calcium, carries alpha radiation straight to cancer growing in bone. And the frontier goes further still. Atoms like actinium that fire not 1 alpha particle, but 4 in a tiny chain reaction inside the tumor. It's not perfect. Aim a powerful atom at a marker your healthy cells also carry, and you get side effects. The salivary glands, for instance, can take a hit. The supply of these rare atoms is fragile, and the science is moving fast. But step back and look at what's happened. We took the thing everyone is taught to fear, radioactivity, and split it into a toolkit precise enough to find a cancer, map it, and then kill it 2 cells at a time. So here's the next question. How does your body build a beam of pure antimatter for a PET scan in the first place? That's the PET episode. It's on the main channel right now. Subscribe, and every week we'll open another machine your body has been inside. Would you trust a treatment that's also a scan? Yes or no? Tell us below.